Continuing on in the investigation of the OceanGate Titan submersible implosion, the Titan sub was equipped with an early warning system designed to protect the human occupants, a patented safety feature known as the Realtime monitoring system. This system of multiple sensors placed throughout the interior side of the carbon fiber pressurized hull were designed to give a series of feedback from acoustic sensors and strain gauges to alert the occupants of the carbon fiber submersible to impending catastrophic damage of the hull. It was supposed to give them enough warning time to be able to resurface to safety before the carbon fiber hull could implode or buckle instantly. But on the morning of June 18, 2023, history was made when the OceanGate Titan sub imploded, leaving the world with questions on how this could have happened. And now that everybody knows how this sub was engineered, we are all wondering how could this real-time monitoring system have failed and allowed the implosion of the Titan sub to progress without warning.
I'd like to be remembered as an innovator. I think it was General MacArthur said, "You're remembered for the rules you break." And I've broken some rules to make this. I think I've broken them with logic and good engineering behind me. The carbon fiber and titanium, there's a rule you don't do that. Well, I did. It's picking the rules that you break that are the ones that will add value to others and add value to society.
So OceanGate CEO Stockton Rush, he broke more than just a few rules. He broke many strands of carbon fiber along the way. So let's take a look at this real-time monitoring system here and try to determine what's wrong. Was there something wrong maybe with the design, with the patent, with the algorithm? Was he ignoring key indicators and alerts in the data? So let's take a look.
Think I'll give this little tug a looky loo. Check for safety violation.
So remember, this version of the hull was version 2, and it is the one that went down to the Titanic and the one that imploded. Now here you can see it's being manufactured at electro impact, and it's being hoop wounded around a steel mandrel. So then the steel mandrel is pulled out of the cylindrical carbon fiber pressure hull, and the ends of the carbon fiber pressure hull are then cut off, as you can see by the red dotted lines there, which the NTSB will use later sort of as witness panels. And these are basically representative pieces that allows investigators later on to come back to the material and look at it and find any manufacturing defects, which we of course know by now that they found plenty of those. Now, one thing that you have to remember here is that this 5-inch thick cylindrical carbon fiber pressurized hull, you can't pierce it, you can't drill any holes into it, you can't do anything to it. It must stay as one whole product. So that's why they have to make this insert sleeve that goes inside the middle of it, which they mount everything else to on the inside of the OceanGate Titan sub. So before they do all of this, you'll see here where they mounted all of these sensors for the real-time monitoring system. And they're glued onto the interior wall of this carbon fiber hull. So we can see here they have 8 acoustic sensors laid out around various parts of the carbon fiber hull. And then to measure the movement of the actual carbon fibers, the strain, they use these strain gauges. And these strain gauges are also spaced around in various parts around the interior wall of the hull of the Titan. These sensors are placed in pairs together, 90 degrees apart. And of course, the NTSB provided us with this handy-dandy lookup table here, showing us where on the hull all of these different sensors were placed. Okay, so Stockton Rush, you know what he's trying to do here, right, with this real-time monitoring system. He's trying to listen for sounds of maybe some cracking of the fibers. So those are the acoustic sensors. And then the strain gauges, he's trying to determine if the material is moving enough. So now the problem with this, though, here's the whole problem I've had with this idea from the beginning, is that this is not a proactive solution. This, ladies and gentlemen, is a reactive solution. So to me, this is almost like the idiot light going off on your dashboard on your car when your car overheats, right? Your car stalls out, you got steam coming out of your hood there. And then if you're lucky and you have a high temp light, that goes on. Whereas in reality, I prefer to see a temperature gauge so I can see long before that there may be a problem and take appropriate action, not wait until it's too close. Now, I want you to take a look at this soundbite here of Stockton Rush speaking at the GeekWire Summit, where he is talking about his real-time monitoring system. He seems to put a lot of faith on these acoustic anomalies that he thinks his system's going to detect, and he's almost making it sound like it's a self-healing type of carbon fiber, which I don't particularly agree with. He thinks the problems are going to go away, which is another scary thought.
Because the pressure and temperature at 1,000 meters and 2,000 meters and 3,000 meters is always the same. And so if it's making noises at that depth that it didn't make on the last dive, then we can stop the dive, we can go up, and we can find out what might have happened. We did work with Janicki, Boeing, NASA. There's 667 layers of carbon fiber in just what's called a 090 axial and rotational layup, which is not normally done, but in the ocean, that's all you see. You don't get any torsional moments.
So it seems that Stockton Rush has a very low aversion to risk, unlike folks like you and me who would be pretty careful. Like, for example, I don't like the idea of jumping out of a plane. And I realize that people want to be innovative and they want to take risks and do some thrill seeking. But even the people that jump out of planes check to make sure that their parachute is packed properly and everything first. It just seems like all of the risk elements were thrown out the window here. Okay, so check out this father and son who were supposed to go on the Titan submersible down to the Titanic, but when they met with Stockton Rush, they didn't like what they saw.
About his project, and he believed everything he was saying. And he said he was coming in on a two-seater experimental plane that he built. And I started to think about, he's coming in on a two-seater experimental plane to pitch me out to go on a five-seater experimental sub that he built down to the ocean floor to see the Titanic. And it was just, he has a different risk appetite than I do. I'm a pilot, I have my helicopter pilot's license. I wouldn't get into an experimental aircraft.
The way this works is, see this green shape right here, this line? So as you start, and if you look down the right side of the screen, it shows you the depth. So you're coming down and you're descending and descending till you get to here, and you're at 3,800 or so meters below the surface. So you're at the Titanic depth at this point, and then you're moving across, just hanging down at that depth for a few hours, and then you begin your ascent back up. And so this right here is some of the noise that they pick up, and they often hear some at the end once they're getting back up onto the Lars and being dragged back up onto the boat, because it apparently is very disruptive to the whole unit. And then the NTSB showed us, after looking through the OceanGate's data log on the RTM system, that 3 of the sensors never recorded any acoustic events during all of the 2022 dives. See, and this doesn't give me a good, warm, and fuzzy feeling at all. This makes me very scared, because now it just seems like, okay, you knew that through all of 2022, it wasn't producing any data, and you're just ignoring 3 data points here. And those could have been data points that maybe, if those sensors were working, maybe they would have been louder and they would have prevented you from going down. And then you remember in a video I uploaded a few weeks ago, I showed you how the NTSB reported this big spike here, this audio spike on dive 80, which is 8 dives before the fatal dive. And so you can see that acoustic anomaly there. And Stockton Rush wrote it off as the carbon fiber hull was reseating itself in the carriage, which makes absolutely no sense to me. And then also on dive 80, the strain gauges reported the same type of response at the exact same time when they all heard that big boom after they came back up from the dive. So now I'm wondering if Stockton Rush was maybe misinterpreting the data or just ignoring it altogether. Because now I'm going to show you how all of the dives after this, we started to see anomalies here in the readings, and they don't seem to be doing anything about it. So it has me questioning whether Stockton was even really looking at these numbers later on after the fact as a post-mortem, and trying to take any types of corrective action for it. So here what they were showing you is 2 different dives, 75 and 80. So 75 is the dark line, and dive number 80 is the blue line, right? So then they're both, look at this, they're like both pretty perfect there. So everything seems normal there, right? Oh, but Houston, we have a problem, because now we're looking between the difference between dive 80 and 81, which is 7 dives away from failure now. And suddenly you're seeing this happen now. So 81 is the red and 80 is the blue. So see how the blue has that straight line that goes all the way down? But if you look on dive number 81 here in that first 1,000 meters, they had a curve there. Something was different there. Remember, dive 81 is the one right after the dive that had the loud bang. So now every dive after dive 80, you can see from 81, 82, and 83, they're all showing this deviation curve. So here's another one of my problems that I've always had here with this real-time monitoring system, is that these acoustic events that we see on the charts here, whenever you hear an acoustic event, what you're hearing really is you're hearing fibers are cracking all over the place. And when a fiber cracks, it doesn't ever just miraculously heal itself. Once a fiber breaks, that's it, folks. And it might even be groups of fibers at a time. Or even worse, it could be delamination going on too. So this is why I think this was the early warning sign at this point. And I believe possibly his real-time monitoring system, if you had paid attention to it, would have saved you. That's the problem there. I think they simply ignored what the data was telling them. It was misinterpretation of the data. So to get an idea as to why Stockton Rush decided not to classify the OceanGate Titan submersible, let's hear from Roy Thomas, who is an engineer from the American Bureau of Shipping, and he's telling us exactly the rules of what you can and can't do with submersibles and what materials you can use and what shapes you should be using. And this will help explain why Stockton Rush decided to sidestep the rules that everybody else plays by.
So typically what we have seen is anytime you go below a depth of 1,000 meters seawater or 3,280 feet seawater, the shape of the pressure hull is spherical. Okay, we have not seen cylindrical pressure hulls being used beyond a depth of 1,000 meters seawater. The reason is a spherical pressure hull is the best shape for resisting external pressure. Okay, the stresses are evenly distributed around the hull. So if you take a spherical pressure hull versus a cylindrical pressure hull of the same thickness, when exposed to the same pressure, you will see that the hoop stress in a spherical pressure hull is half that of a cylindrical pressure hull. Okay, so if you see a cylindrical pressure hull being used beyond 1,000 meters, it is pretty unusual.
So you see this? You have the American Bureau of Shipping, who classifies all the boats and the submersibles, telling us directly that a spherical pressure hull vessel will far outperform a cylindrical shaped vessel, and that the cylindrical shaped vessels are not even normally used below 1,000 meters.
The important thing is this code states that for a new construction pressure hull, no delamination and no cracking in the matrix is permissible. Okay, so if you have a new hull with delamination or cracks, it is not acceptable as per this code.
Now, I've showed you on some of my previous videos in the last couple of weeks on the Titan implosion, how when they found the debris down at the bottom of the ocean floor, a lot of it was just severely cracked and severely delaminated. And of course, later on, the NTSB showed us those pictures that I've showed you too, with all of the voids, those huge voids and bridges of voids as well in the adhesive. And these types of manufacturing defects are not permissible at all by the ABS classifications. So had he gone for classification, all of this could have been caught early on, and the entire implosion might not have happened had they taken corrective action.
So one of the very important failure modes for thick shell carbon fiber composite sections under external pressure is snap-through buckling. Okay, now snap-through buckling is an effect that has been observed in subsea pipelines made of glass fiber reinforced plastics. Okay, now this buckling causes sudden and catastrophic failure of the pressure hull. Okay, and it is thought to be triggered by shape imperfections. For example, if there is out of roundness, that can trigger this buckling. Okay, now snap-through buckling is different from traditional buckling, which is caused by progressive overpressurization of the pressure hull beyond its design depth. So when snap-through buckling occurs, it causes instantaneous delamination of the pressure hull and instantaneous collapse of the pressure hull, which can occur in less than a millisecond. Okay, so if you have sensors for real-time monitoring, it will not pick up any signs of this failure before it occurs. Okay.
So when he's talking about this buckling, and this is the failure mode that I think actually happened, I don't think this was a progressive, but it just seems like it came out of nowhere. You remember, they sent that last transmission that says, we're dropping 2 weights. That just means they're slowing down. They're getting ready to go near the bottom. They had no indication that anything was giving them any type of problem, and it just, boom. happened just like that. And that's the way a buckling failure occurs. And when you look at the hull sitting there on the bottom of the ocean floor, it has a large buckle in it.
So under the ABS underwater rules, carbon fiber pressure hulls are not acceptable materials for submersibles.
This is OceanGate testing a 1/3 scale model of the original, I guess you could call it, they called it Cyclops at the time. This is the carbon fiber hull. And here you can see they put the RTM sensors in there, and you can see it actually running on the computers as they're collecting the data off of it.
It's a test.
The biggest test we're going to have for some time.
Under so much pressure,
Gets the heart pounding.
it has to be done at night. Tony's setting up sensors inside a test hull about 1/3 the size the real one will be. Then he'll put it into a pressure chamber to simulate diving in the ocean.
Nice. But before we do that, we want to make one last check that we can communicate with the instrumentation inside.
Those sensors are key to Stockton's entire project. During the test, they'll hopefully let him know if the hull is about to implode. A crucial heads up to get out of Dodge.
You want to know that when you do hear a pop or a crackle or a noise from the hull, that gives you sufficient warning. It shouldn't be the case that at 3,000 meters it's dead quiet and then the hull fails a few moments later.
Not knowing when a carbon fiber hull is making normal sounds, or sounds that mean it's about to crack in half, is one reason it hasn't been used before in manned subs.
And I think we may have solved it with our real-time monitoring system.
There's only one way to find out what a hull failure sounds like. Put the pressure on.
So we're holding at 2,000 psi.
So here you can see the RTM system collecting all of the data.
The question is not as much when it fails, but that we have sufficient warning to be comfortable that when you put people in the sub, you won't have a quiet hull and then a failure.
But at what pressure will that be?
The acoustic measurements we will see on the monitor in what would look like an Excel spreadsheet of data flying across the screen. But we will not hear anything. Sometimes you hear a little bit of cracking if they're pretty big events, but if we go to failure, then we'll all hear it.
It's many sticks of dynamites of energy, so it's like having your head next to a shotgun and you don't know when somebody's going to pull the trigger. It's been relatively quiet at 6,000, so we're going to go up to 6,500. Shall we? 6,500. New territory. I would say that was it.
The model imploded at 6,500 psi, about 15,000 feet underwater.
Yes. Well, this will be interesting. Let's see what she looks like. We had an extremely loud implosion, shook the building. We had seen a number of acoustic events in increasing intensity, and that's where it failed, was 6,500.
The next step is to crunch the nearly 1 terabyte of data that they got.
As we analyze the data more, we'll be able to trace the fingerprints of a failure way in advance of when it happens.
If Stockton and Tony can do that, today's failure will be a huge success.
So now we see that the 1/3 model finally imploded at about 6,500 psi, which is probably why Stockton Rush didn't think that there was any problem ever going down to the Titanic depths, and which could be one of the causes, I think, of why he might have ignored some of the other warning signs coming from the RTM data. He simply didn't think that it was an issue until you get to 6,500 meters. Okay, so here is Stockton's patent on the real-time monitoring system, and you can see there's his name right there, Richard Stockton Rush III. He's got his diagram, and he shows the acoustic emission detector on the interior locations, and he also shows the strain detectors on the interior locations in various places. The present disclosure also relates to methods and systems for analyzing data, determining background conditions, assessing and validating the health of a composite material or structure, determining alarm conditions, and predicting failure conditions, and the like. Yeah, so right here it says programmed alarms and notifications may be implemented to alert an operator when and if the vessel or component of the vessel is compromised or in potentially unsafe condition. So right here, the main core of their algorithm, you can see right here, it says, in some embodiments, methods and systems as described herein compare real-time acoustic and or strain measurements acquired during a current operation with acoustic operation, right here, see, of the same composite structure. And then here he says it's compared, for example, to values acquired during a previous operation, right there. These would all have to be real-time values at the same, right here, or similar vessel depth acquired during previous dive of that vessel. So you wouldn't want to use, for example, a dive down to the Andrea Doria, because that's only, however deep that is, a few hundred feet. You would have to compare the data from a previous dive down to the Titanic in this case. Okay, so here's my take on why I think there are some of the reasons why the real-time monitoring system failed here on the OceanGate Titan sub. Well, first of all, here, the main item is they went with a big old cylindrical hull instead of a spherical hull. If you'd done that, maybe, just maybe, things might have turned out different. And then you wouldn't even need the real-time monitoring system. The other problem, too, with carbon fiber is that we don't have a solid database of previous testing by standards bodies or third-party labs. And so you can't just go and use off-the-shelf software or really pretty much anything to help determine what parameters you're supposed to use to determine, hey, if I go past this threshold of a voltage, does this mean that the sub is going to implode? So right off the bat, it looks like they just went with whatever Stockton wanted to go with. And we don't know if he made bad assumptions or not. Also, you had 3 channels not producing any data. Could one of those channels have been one that would have given you the necessary alarm? You never know. Also, if you remember, Boeing at one time had suggested going with a 10-inch thick hull, the thickness all the way around. And Stockton Rush had dropped it down to 5 inches. So I've always wondered, hey, if they had left it at that original 10-inch thickness, do you think maybe it would have been more resilient to the pressures and you wouldn't have all of this fatigue that it wouldn't be able to push in and deform the shape or maybe crack any fibers? So that one still bothers me to this day. Another issue you have here is, what about possible problems with the autoclave process? Remember, they had to wrap this carbon fiber 1 inch at a time and then stop. And they had to make 5 trips over to Janiki Industries there to put this thing into an autoclave. So remember, you have to bag it, transport it by truck, put it in the autoclave, transport it back. And man, a lot of things can go wrong there. So one of the things, too, you can look at is maybe the real-time monitoring system algorithm is flawed itself. Maybe it's insufficient. You know, you're choosing random layers of sound level to trigger an alarm. And who sets these arbitrary numbers? Stockton, and it's based on what criteria? So we don't have any basis for that. I think also that Stockton Rush put way too much faith in the fact that he had a patent on his system, which may have been flawed to begin with. And the reason why I think it's flawed is because it is more reactive type of engineering than it is proactive engineering. So even though Stockton Rush thinks we're getting enough advanced warning, apparently we were not getting enough advanced warning. And maybe he didn't know that buckling failures give 0 warning. One thing I've always wondered too is, do you think maybe they could have just gotten some kind of metal rings and just added a little more support near the ends and maybe in the middle as well? For example, here's our carbon fiber hull. And so what I was proposing is, let's say you got some metal rings and you put one sort of right here near the end to help support it a little bit so it couldn't be pushed in that much by the pressures. And then maybe you do one in the middle as well. And then you do another one here on the opposite end. So I think that this might add some more additional support to the carbon fiber hull. Now, if you want to binge watch all of the videos that I've done here on this channel on the Titan sub, you can go to my homepage here on YouTube and you can type in Titan and search, and it will give you all the results of all of the Titan videos I've done. And I will also put a link down in the video description to some of the more recent videos that I've done here on the Titan. Also, make sure you check out this video over here on the FIU pedestrian bridge collapse. That's probably one of my best engineering analysis yet. And then after that, make sure you check out this other video here that I did on that kitchen remodel with the double-decker cabinets and the 45-degree refrigerator. So thank you so much for joining us, folks, today, and keep those questions coming, and we'll see all of you on the next one.